Okay, so this video is going to be just a little bit different than the others. I recorded this and for some reason the video was corrupted, but I've got the notes here, so I'm going to go through it, and I'll go through it slowly so you have time to write things down as you need to. Hold on. Oh, there we go. Okay. So just a reminder, I'm going to start here. Resistors add in series, and we just use a plus sign here between the resistors to indicate both the mathematical operation and the fact that, and to give some shorthand for when we're writing down something that one resistor is in series with another. Okay. When resistors are in parallel, remember we have that awkward that the equivalent resistance is the inverse of the sum of the inverses. And so we don't have a mathematical operator that will do that. And so we use this set of double parallel lines in between the resistors. So here R1 is in parallel with R2 is in parallel with R3. So that we have those long parallel lines. Remember that is equal to this equation, the sum or the inverse of the sum of the inverses of all the parallel resistors in that particular string. We also talked about that we have a shortcut when we talk about just two resistors. R1 in parallel with R2 is the product of the two resistors over the sum. So oftentimes what I'll get students doing is they'll be working quickly and not think this through. And when we have three resistors, you'll try to just extrapolate to this two resistor case. So R1 in parallel with R2 in parallel with R3 does not equal R1 times R2 times R3 over the sum. It's not the product over the sum for more than two resistors. Okay, so this is wrong, as I've noted. This is not okay. So, but what you can do, and I like doing product over sum just because as you see more and more resistors, you get to, in parallel, you get to see certain patterns and can do these kind of in your head. If you have three resistors in parallel, like I have here, this 15 ohm, this 10 ohm, and this 6 ohm resistor, all in parallel, and I know that because there's a node here, which they're all connected to, and a node here in which they're all connected. You don't have to worry about what this means. These are just open terminals. No current can flow through them because they're an open circuit. But it just shows that they're not just three things sitting out there alone. So you can combine the resistors in pairs. So and then keep adding one new resistor to the resulting pair. So I started by looking at just the two resistors, 15 in parallel with 10. So the product over the sum for that is this 150 over 25. And so that results in a resistance, an equivalent resistance of 6. Okay, so now I can redraw this, and as you get more comfortable with this, you won't redraw as much as you'll just do this in your head. Then we'll have, I'll replace the 15 and 10 ohm resistors with this parallel combination of 6. So it just goes right back in between the two nodes there. Then it's in parallel with the other 6 ohm resistor. And so the equivalent resistance now is going to be the product over sum of these two, 36 over 12 or 3. So you can do two at a time and just keep adding a new one in, and you can do product over sum, or you just could have done one over the sums of all of them using the equation like this one here and got it at one time. It's up to you. Okay, so once we understand how to combine resistors in series and parallel, we can add a tool to our circuit solving toolbox that I call simplification and expansion. So when we have a circuit, typically a single source and a bunch of resistors, and we simplify it down to the simplest we can get, which is often the source and a single resistor. And then we expand back out from that simplification and solve for voltages and currents as we go using Ohm's law. Okay, so we're going to do that here. So I've got this equation here, or the circuit here, and I'll give you a chance to draw it. But it's a 20 volt source, a 7 ohm resistor, a 12 ohm resistor, this 20 ohm resistor, this 2 ohm resistor, and the 3 ohm resistor. And we have two quantities here that we're going to solve for, Ix with this direction and Vx with this polarity. Okay, so I'll give you a second to draw that. I'm going to take a sip of water. Okay. So I want to point out two things about making combinations. So making a combination here, like we did, is kind of simplistic. But in a real circuit, when we start to combine elements in series and parallel, we have to account for how it changes the circuit and how it changes what we know about voltages and currents in the circuit. Okay, so if we read this first line here, when resistors are combined in series, we lose a node, the node in which those elements were connected, and we lose information about the individual resistor voltages, but not the current, because the current's the same whether we're talking about two resistors in series or the equivalent resistance. Okay, the dual of that, we often call this the dual when something is kind of the same but opposite. For resistors that are combined in parallel, we lose the individual current information associated with those two resistors. We do not lose the voltage information, and we don't lose any nodes. Okay, so these two are important, and I'll refer to these again as we go through this particular circuit here. So if we're going to simplify and then expand a circuit, I like to start with the circuit by identifying the nodes, all of the nodes, and then numbering them. Okay, so there's a node here where the two elements come together. I've called that node 1. There's a node here where these four circuit elements have come together. I'm going to call that node 2. There's this node where these 4 circuit elements have come together as well. And then we have this node here where the 2 and the 3 ohm resistor come together. I've called that node 4. Okay, so we're going to solve for Ix and Vx by simplifying down to a single source and a single resistor, and then expanding back out by writing Ohm's law. So I'm going to come down here. I've redrawn the circuit just so we can see it. And what I'm going to do, or what the first step to do, is to start thinking about what is in series and what is in parallel. Okay, and I always like to start kind of at one side of the circuit and work my way towards the source. So if we look at this circuit, there are 2 nodes that only have 2 connections. And so whatever elements are connected at those 2 points are in series because there's no other place for the current to go. So we can't combine a voltage source and a resistor. They aren't like elements. So node 1 is not terribly important to us. But at node 4, we have 2 resistors connected in series, and we can combine them. Okay, and we'll combine them 3 plus 2. Okay, and so what I like to do is I like to draw the circuit that draw the parts of the circuit that we haven't done anything to yet. So if you look at this part of the circuit here, we look to the left, none of that has changed from the previous circuit. So I like to draw that first, okay? And then I'll add the part that is simplified later, okay, at the end. So this 3 ohm and 2 ohm series combination, when we combine them, we are going to lose node 4. Node 4 is going to be gone. It's going to be kind of embedded in that equivalent resistance. Okay, so that equivalent resistance is going to be connected between node 3 and node 2. Okay, where node 4 has disappeared. So I've added that 3 plus. And I'm going to have you hold on for just 1 second because some of this isn't going to make sense as we're going through. Give me just 1 second. I'm going to do some erasing and we'll come back and we'll add this stuff in later. So my apologies, but this will make more sense if I do this now. So just give me a moment to do some fixeroo in here. That way I can do some more writing too, which may be helpful. Okay, so going back to here, thank you for indulging me. Going back to here, we've connected this 5 ohm equivalent resistance between node 3 and node 2. Okay, we don't lose Ix. Remember, I'm going to pull up here. Remember, when resistors are connected in series, we lose a node, and we did. We lost node 4. And if we were looking at individual voltages for either one, the 2 or the 3 ohm resistor, we would lose those too. But we're not going to lose the current. So we can draw the current Ix on this circuit. because it still exists. Okay, so here's the first step in our simplification. Now we're going to do it again. We still only have one node with two connections. We know we can't do anything at node 1. There's no simplification here. But if we look between node 3 and node 2, we've got the 12 ohm resistor, we've got the 20 ohm resistor, and we have this equivalent 5 ohm resistor. So between node 3 and node 2, we have 3 resistors connected in parallel. Okay, so I've got REQ is equal to 12 in parallel with 20 in parallel with 5. And I've done these in pairs, so I've combined 20 and 5 in parallel, and I get 4. And then I put 4 and 12 in parallel and got 3. So that's our equivalent resistance. Okay, now that the resistance, remember for when we have elements in parallel, we lose only the individual current information. We don't lose voltage and we don't lose nodes. So my equivalent 3 ohm resistor is going to be connected back between node 3 and node 2, just like it is here. Okay, we didn't lose any voltage information either. So the voltage across the 20 ohm resistor, by nature of the fact that these are in parallel, is also the voltage drop across the 5 ohm resistor, and it's the voltage drop across the 12 ohm resistor, and it is the voltage drop across all of the resistors in parallel. The negative terminal here of the voltage is at node 3, and the positive terminal of the voltage is at node 2. And so that's exactly what we have here. We have that 3 ohm resistor connected between node 3 and node 2, and we have that voltage Vx, negative terminal at 3, positive terminal at 2. Okay, but Ix we have lost. We cannot translate Ix and put it on the circuit because when we combine elements in parallel, we lose the individual current information. So Ix doesn't live on this circuit. There's nowhere for us to put it. Okay, and that's probably one of the hardest things to really comprehend and get comfortable with as you combine elements is that some voltages and currents won't appear as you simplify. Ix is one of those here. Okay, so this is our next simplified circuit. So we're going to simplify again. And again, we're going to look for series or parallel connections. All of our nodes now have only 2 connections. Okay, so at node 1, again, we have 20 and 7. We can't do anything there. At node 2, we have 20 and 3. Can't do anything there. But at node 3, we have 7 and we have 3 ohms connected in series. And so we can make a simplification, 7 plus 3. We will lose node 3. Okay, we will also lose the voltage information because we lose voltage information on the individual resistors. Okay, so we will pull down to this next circuit where I've got, and I'm going to erase one more thing. We'll come back to that. Oops. So we will come back to this here. And so we have the 20 volt source and the 10 ohm resistor connected between node 1 and node 2. Node 3 is gone, and we have this 10 ohm resistor. Vx is also gone because we have lost the individual voltage information. And so this is our most simplified circuit, the 20 volt source and the 10 ohm resistor. Okay, 2 elements. Whenever we have 2 elements in a circuit, they are both in series and in parallel because there's the only 2 elements in the circuit. Okay, so now I will go back to starting to write here. So we get to this point, we finalize, we have a single source and we have a single resistor, and now we're going to do the expansion. And so now we're going to work backwards. We're going to go back up through the circuit and we're going to solve for things. And that's what I was erasing before, so we can see that now. Okay, so what I need to know is the voltage and current across this 10 ohm resistor. Now, the voltage is easy. We've got a 20 volt source in parallel with the 10 ohm resistor connected between the 2 nodes 1 and 2. So this also has to be 20 volts. Okay, but 20 volts doesn't really help us. Okay, the current would though. Okay, so I'm going to solve for the current, and I'm going to solve for the current flowing out of the 20 volt source. Okay, I want passive sign convention to hold as much as possible, and so I'm going to choose that here. This is the only source in the circuit, so the current's got to be flowing from minus to plus through the source, and then it will end up flowing from plus to minus through the 20 volts across the 10 ohm resistor. And so now I can solve for the current I1 just by writing an Ohm's law equation. It's going to equal 20 divided by 10, or I1 is equal to 2 amps. Okay, so now we have 2 amps flowing through the 10 ohm series combination. So let's go back a step. We're going to pull up to this circuit, and I want to label I1 on this circuit. As I expand back out, those currents and voltages are very easy to see on the circuit. Okay, so I1 is still the current flowing out, out of the 20 volt source. Here's still I1. Okay, so I1 is going to flow through the series combination of resistors, and now we can use it to find the voltage Vx. By Ohm's law, Vx is equal to 3 times the current flowing through it. That current's going to be I1. Okay, but that current I1 is going to flow from minus to plus. The passive sign convention isn't holding because it's based on the way Vx was given to us. We didn't choose it, so this is what we have to work with. So I'm going to have to put a minus sign in front of the 3 there. The minus sign turns the current I1 around, so the passive sign convention holds, and I will get that Vx is equal to minus 3 times 2, or minus 6 volts. Okay, now I'm going to go back again, and I'm going to come to this circuit here. Okay, I know what Vx is. Vx is minus 6. It exists on this circuit. Okay, I can draw I1 on this circuit if I want to. It's not useful anymore for finding Ix. That's the only thing we have to solve for now is Ix. Okay, so I'm going to come back to this circuit here, and I'm going to use Vx to find Ix. Okay, so Vx is the voltage drop across the parallel combination of 12, 20, and 3. So those 2 resistors are in parallel between 3, or those 3 resistors are in parallel between 3 and 2. So if they're all in parallel, that means that this voltage here is also Vx, the voltage drop across that 5 ohm resistor. Okay, so now I've just got a nice little Ohm's law equation, although I wrote over what I was trying to highlight there. We've got a nice little Ohm's law equation here. Okay, so by Ohm's law, I'm going to write that Ix, that's what we're solving for. Ix is equal to Vx over 5. Okay, but again, the passive sign convention isn't holding. Ix is flowing from minus to plus. So we're going to change the sign on Vx to fix the passive sign convention. And so Ix is equal to, and I've forgotten what it is already, minus 6. Minus 6 divided by 5, or this is going to be minus 1.2 amps. Okay, so we've used simplification and expansion to simplify the circuit down and then expand back out. Now this may seem like a lot of work to draw these circuits and simplify and draw new circuits and then go back. And it is a little tedious, but as you get more comfortable with this, you will find that you don't have to do all of this extra work. You can do one simplification probably all at one time and then expand all at one time and figure out what's going on. But this is a great way to see how voltages exist in a circuit and how they and how currents exist in a circuit. Okay, so again, this isn't a technique. I wouldn't say solve the circuit using simplification and expansion as part of, say, an exam, but it certainly is something that's useful, especially when we start talking about superposition, where in superposition you will be solving subsets of a circuit with a single source and a lot of resistors. And so this method can be very useful for that. Okay, so that's all for this lecture. Hopefully this video will be okay, and the next lecture will start in a little bit.